Okay, we're recording now. So, hi everyone. We will today go back to strong. I thought we would go to strong induction and just go about over more inductive proofs. So rather than start something, okay, not completely new, but let's just ground it. Um, uh, Audio is staticky. Ouch. Okay. That's bad.
How about this? Is this better? Is this better? Oh, okay. Good. Hey, I got some headphones to replace some older ones, and apparently they're junk. Okay, so we'll go over more. Thanks for heads up. So we'll go over more inductive proofs and strong inductive proofs today. I thought that would be the best way to spend our time. So, by the way, the test next week is about basically everything that is happening until today, right? So it's logic, sets, functions, and induction and strong induction. Yeah, so you're saying that the video is not the best and it's lagging. Like, I really cannot do much about this right now. I'm connected to a wired thing. Yeah, I think it will be intermittent. Yeah, it's possible that my wireless is actually better than my wired, so we can try that. Okay, when it gets bad, I will try that. Okay, so so let's go over this over some more strong induction proofs. Okay, let's go to it. So here's the last one we were looking at. Generalization. I mean, okay, just another example of 5 or 7 stamp. You have two quantities, in this case 5 and 7, and we want to argue that every integer from 24 up can be created using multiples of 5 and 7s, right? So let's jump to it. Let's just zoom a little. Okay. Okay. So the statement is, so claim is this: for every n greater or equal to, and it's too dark. Maybe that's better. For every n greater or equal to 24, there exists ij such that n can be expressed as 5 times I plus 7 times j, right? So that's a statement that any amount greater than 24 or equal can be expressed using 5-cent stamps, namely take I of them, and 7-cent stamps, take j of them. Where is the predicate? Why is this a statement that can be stated in a form proven by induction at all? So this is the predicate. This is the P of n. Okay, so your statement is of the form that for every n greater or equal some integer, P of n, P of n is a predicate specified by a quantified Boolean formula. The formula says there exists some ij such that n is expressed by that sum, right? But that's a predicate about n. For every n, this quantified expression is either true or false. We are claiming that it's true for all n greater or equal to 24. So proof by strong induction. Okay, so first base case and of course the inductive case, inductive step. And basically one way to figure out what needs to happen here is maybe uncharacteristic. Okay, so you can check, is P at 24 true? Okay, yes, because 24 is 5 times 2 plus 7 times 2, right? Is P25 true? Yes, because 25 is 5 times 5 plus 7 times 0, right? And basically, how many shall we check? Let's see how we would do the inductive step, and then we'll know how many we should check here. So here's the idea of the inductive step that is the same one, from the similar proof for some other parameters, which were, I think, 3 and 5. So inductive step has to show that for any k greater or equal to 24. Okay, my internet connection is unstable, so you guys, hopefully it will fix shortly. For every k greater or equal to this initial value, if the predicate holds about all integers up to the kth one, then all of this must imply, that's what we want, that the statement is true about k plus first. That's the form of the strong inductive proof always. I mean, the only variable thing is here that we started at 24. Other than that, it's always the same format. So, okay, so this is what we want to prove. Okay, so to show pk plus 1, i.e. that there exists some ij such that k plus 1 can be expressed as 5i plus 7j, it would suffice if we knew that k plus 1 minus 5 was expressed as 5i prime plus 7j prime for some I prime j prime. And why is it? Because basically, okay, you want to express this as a bunch of 5s and 7s. If it was true that you could express 5 less as a bunch of 5s and 7s, then you would express k plus 1 as a bunch of 5s and 7s, namely, because then k plus 1 can be expressed as 5 times I prime plus 1 plus 7j prime, right? So this would be our I that we need, and this would be our j that we need, right? So in other words, because of the simple move, it turns out that p at k plus 1 minus 5 implies p at k plus 1. that's what this says, because this is p at k plus 1 minus 5. And this is, of course, pk plus 1, right? So we just argued that this thing would imply this thing. And that's exactly to argue that this implies that. So, so this k plus 1 minus 5 is k minus 4. So this is the same as to say pk minus 4. And now we know how many base cases we need, because basically our argument will be good as long as pk minus 4 existed somewhere in here. Then this conjunction would imply this, because the conjunction would include the only thing we really need, which is that p holds at index k minus 4, which is 5 less than this. So we just have to make sure that this range always includes k minus 4. And how could it always include, right? Well, basically, okay, you know what? No, so here I made a mistake. This, I actually cannot do this for k equals s to 24. At this point, before I reached here, I basically didn't know what this threshold value is. This is the specifying the threshold value is exactly specifying how far do I need to go in base cases before I have some inductive argument that would kick in afterwards. So how many base cases are needed for this inductive step to kick in? Well, basically, I cannot use this inductive step for 26, because the step, do you still see this? Okay. Maybe I need to.
The camera view is kind of blurry. Could you try stop sharing your PC screen so you're only sharing the paper? Maybe that will help it be more clear.
It is, I think, stops sharing, right?
I think so. It's still kind of blurry though.
Yeah, I can't really read it.
Okay. It looks good on my screen. It's focused on my screen.
Darn video compression.
Okay, so the video compression is screwing this up. Okay, let me try wireless and see whether that improves it.
No, it's a little blurrier now.
Now, my wireless claims to be fantastic. Hold on, I can try to switch to a different wireless and see whether that might actually screw things up, but okay. Seems like I'm on a different wireless network now. Okay, did the video improve in any shape or form?
Not really.
So today is different, right? Like usually when I do this, it's you can read or no. When I watch these YouTube videos, I can read on those. So today is extra blurry, right?
It seems both out of focus and compressed. Okay, no, go back. Okay, I think that's in focus. It's a little better, but it's still weird and blurry. Okay, I can't read the cursive.
Okay, not sure what to do about this. So yes, I must have a bad connection, or because on my screen it's very crisp, so it is in focus, but it is not showing. So I guess because I'm recording on locally, so eventually it will be correct resolution. I guess that's why when I watch a video, it looks good afterwards.
It's a little better right now. I don't know if it's going to dip in quality in a second, though.
Yeah, this is good right now.
Oh, okay. Okay, so something has improved about the connection.
I mean, it's a little bit better, but it's not great.
Okay. All right. So, okay. So, okay, where were we? If what we basically the whole thing established that p of k plus 1 would follow from p k minus 4. So now the we need k minus 4 to be always in this range, and this will tell us how many base cases we need to have. So let's say that we wanted only to have 24 and 25 as base cases. Could we argue this for k plus 1 equal 26? Well, no, because if k plus 1 is 26, then so would p26 follow from this? If k plus 1 is 26, then k minus 4 is 21. And we don't know about 21. In fact, we started here, well, actually 21 happens to be true, but the problem is that 23 is not. So we need to add p26 to the base cases. Okay, so we need some integers that would make this true. So 1, 5 is 21 here, so it would be 3, right? Now, what about p27? So p27, if k plus 1 is 27, k minus 4 is 5 less, so it's p22. Again, it's outside. So we cannot use that. We cannot argue p27 by the inductive formula because basically the starting point here would then have to be 26, and therefore this would not guarantee to include this k minus 4th element. So we need to show this by hand, right? And it's okay because it's 5 times 4 plus 7 times 1, right? And likewise, we still need 28 because 28 minus 5 is again outside of this range. So we need to argue this guy by hand as well, and that's fine because that's 5 times 0 plus 7 times 4. And after this, we are good because at 29, if you subtract 5, you're gonna get to 24. So once all these are in the base cases, then you know when you can start using the inductive step, and it's at this threshold, right? You can make this argument only if this guy falls somewhere here, which means that you have to make this at least 28, or otherwise you will not guarantee that 5 steps back still falls in this line. So it is an example where it is not obvious how many base cases need to come here. The number of base cases kind of came because we had this very simple inductive argument, but the inductive argument told us that basically how far back you need to look up when you make this argument. And this told us how many base cases we need for this formula to start kicking off and proving it for every other integer after this threshold. Questions? Okay, I will move to a different proof example. Okay, so here's another thing I want to prove by strong induction. So you have assume that a chocolate bar consists of n squares, okay, and it's a chocolate bar is a rectangle. Okay, it has some number of columns, some number of rows. They make n. Breaking a chocolate bar consists of picking any horizontal or vertical line and breaking along that line. You then make 2 chocolate bars and you recurse. So you pick one of these chocolate bars and the ones you got, right, of breaking, and you keep breaking it in the same way. So you have to pick some horizontal or vertical line, break it along this line. Call the function b of n the function that tells that how many breaks, how many of these cutting actions do you need to break a chocolate bar. Now, it is not clear that for any n, this number is unique, that this is a function, because perhaps for some chocolate bars with n of size n, you can break it with some number of cuts, but a different bar with a different geometry, let's say a perfect square where n is a square, right? So can be broken using a different number. But here we're going to claim that that this number is fixed, that it doesn't depend on the geometry of a chocolate bar. So let's look at the square chocolate bar. Here would be a cut, and now you create 2 bars, and you recurse. And how can you cut them? Well, you have to cut this one, and then you have to cut, now you have 3 pieces, and then you have to cut this one, and you will have 4 pieces, and you're done. So the number of cuts was 3, and you can sort of see, okay, it wouldn't, by symmetry, basically, it doesn't matter if you start with a horizontal line, right? You will always get a 3. Okay, how many, a 6-piece chocolate bar, how many cuts do you need? Think a little bit. Right, that does not seem to be a way to cut it without 5 cuts. So I can do 1, 2, and then I have 3 of these little pieces, but then I have to cut each of them. So it's 2 plus 3. Or I can cut here, that would be 1, and then I have to cut this guy with 2 cuts and this guy with 2 cuts. So 1 plus 4, again 5. Here is a theorem Okay, and maybe okay. So I was gonna do it on paper, but we can do this on the slide instead. So the theorem is that you need exactly n-1 cuts. It does not matter. The geometry of the square does not matter. Sorry, of the square of the chocolate bar. And okay, so let's. This is a strong proof by strong induction. Base case n equal 1. There is no breaks necessary, so therefore the number of breaks is 0, and that checks out with this formula, right? Because for n equal 1, this formula resolves to 0, as we claimed. Okay, now inductive step. This is a strong inductive step. Suppose that for any threshold, and indeed in this case, because my base case I only proved 1, I will claim that the base case already works if you start at 1. I mean, the inductive formula will already work if inductive step will already work if you start at k equal 1. If the predicate, oh, by the way, what is the predicate on n? The predicate on n is the green thing, right? Which says the number of cuts that are necessary to cut a chocolate bar, any chocolate bar of area n, is n-1. Okay, so that's the predicate. So suppose the predicate was true about any I in the range from 1 to k. That's the strong induction assumption. And so the predicate is true, meaning that the number of cuts for I-sized chocolate is exactly I-1, and that holds for any I in this range. And we want to argue, because we're ending at k, the hypothesis part, that the predicate holds for k plus 1. And what is the predicate? It's here. That's the predicate for k plus 1, right? N equals k plus 1 in here. Right, so in other words, we argue that k plus 1 sized chocolate requires exactly k cuts. And here is the inductive proof, and you see the strength of strong induction right here, because regardless how you cut this k plus 1 sized bar, you have to cut it in 2 pieces using some cut. And the only thing you need to know is that the cut divided into two sized chocolate bars. Let the size of the first one be k1, the second be k2, but obviously they have to sum up to k plus 1, right? Otherwise, it's like you have eaten some pieces while you were cutting, right? Now, by inductive assumption, these two sizes of these 2 pieces are, first of all, non-zero, right? Because they were, otherwise the cut is not a cut. So they're both greater or equal to 1. And also, they are at most k, right? Because if one of them was k plus 1, then the other would be 0. So they fit in this range. So therefore, the inductive assumption that the predicate held on any integer in the range applies to k1 and k2, whatever they were. It doesn't matter how you cut this k plus 1 sized chocolate into 2 pieces. So you can apply your predicate for both k1, k2, and which means that after you perform this cut, no matter how you cut this piece, the number of cuts will be k1 minus 1. That's what the assumption said about any integer in this range. And likewise, no matter how you cut the k2 sized piece, the number of cuts is k2 minus 1. So you now just add the cuts, 1 to break this guy into these 2, k1 minus 1 to break up this guy, k2 minus 1 to break up this one, and then they sum up to k1 plus k2 minus 1, and k1 plus k2 is k plus 1. Sorry. And k plus 1 minus 1 is k, which is what you needed. Again, be careful with your variable name choice. If we try to do this proof using n instead of k, you could, except that you're sort of more likely to make a mistake by comparing what the predicate says in general to what the predicate says for your variable right here. If you name this the variable that is an index of induction, which is k here, the same as the variable in the predicate, you might make mistakes easier. Okay, that's the only reason why we use a different variable in here. Okay, so a very general statement, very easy proof in the end, right? Once you see the strong induction working, it also you see the power of it. It did not matter what these guys were. They fell into the range, therefore the inductive assumption kicks in for them. Any questions on these, on this proof? Okay. So let's move a new example. K2 greater or equal to 1. Yes. K2 greater or equal to 1. Can I explain the last line? Yes. It was right here. Both of these guys need to be in the range. There is no difference between K1 and K2. They're symmetric. Whatever is true about the range of one is true about the range of other, right? Because indeed, when you cut, there is no reason, you can just rename them. So both should satisfy the same constraints, and these are the constraints. Can you explain the last line? You mean this one? It's arithmetic. So okay, this is the one. So how many cuts I needed? One cut is this one to divide the top bar into these K1 and K2. That's the cut. This is the cut implied by the assumption that K1 sized bar requires this many cuts. This is the number of cuts that were implied by the assumption that K2 sized bar has this many cuts. And now I'm just adding all these cuts. And so 1 minus 1 minus 1 come out to minus 1. K1 plus K2 is K plus 1, because these two were the two pieces into which I divided a bar of size K plus 1. Notation-wise, you can ask, why do I have K here? Could I have K minus 1 and instead claim the statement about K? And then this is, go ahead, it's the same. You can. These are sort of arbitrary notational choices. I can rewrite this proof where I used a variable K, which just has to be greater or equal to 2. Here I would have K minus 1, and here I would have K and K minus 1. Perhaps that would be even a clearer choice for this particular proof where your predicate is this way. So this is an arbitrary choice. It's up to you. Just don't mess it up by somehow assuming this up to K minus 1 and yet proving about K plus 1, right? So you have a gap. Okay, here is a different proof, different kind of statement. The statement might be known to you that every positive integer can be written as a sum of powers of 2 and distinct powers of 2. So for any integer, you can represent it as 2 to some power plus 2 to the next plus 2 to and for some distinct integers. There is even a stronger statement true. This is true for integers that are for distinct integers. Yes. This fact is basically the same fact that says that n can be expressed in binary, because binary representation is nothing but you take bits and they tell you which power of 2 you should take. If the bit is 0, you ignore that power of 2, and if the bit is 1, then you take that power of 2, and then you just recurse by powers, right? So this is the same statement, and we'll go into representations of integers in different bases soon enough, later in this class, where we will refer to this. So let's check. 17 is the bunch of powers of 2. Yes, it's 1 plus 16. So these are the powers of 2. And don't forget, 0 is an integer. 2 to the 0 is 1. 31. It's 32 minus 1, which is 2 to the 5 minus 1. So if you remember the formula for sum of geometric sequences, this is the sum of a sequence of powers of 2 all the way to 1 minus this. So 2 to the 5 minus 1 is this summation. Okay, and you can also check this by hand, but it is true by the general fact of if you sum up a geometric sequence, that sums to the next power minus 1 over the base minus 1, but the base is 2, so that division is a division by 1. Okay, like one more, 22, that happens to be 16 plus 4 plus 2 again, right? So why is this true in general? The book has an alternative proof of this. The proof actually uses what was this principle called? Oh, geez, I just blanked out. The principle that says that every set of integers has the smallest one. It's equivalent to induction, and they use it explicitly to show this. We will have a slightly different proof. It's good to see two versions. So here is hold on a second. This screen stopped going. Here is the proof. So here is the theorem again, right? It says that every integer can be represented as a sum of distinct powers of 2. In other words, it's a sum of some 2 to the I1 plus 2 to the I2 for some distinct integers. Let's check some base cases. N equal 1 is a power of 2. N equal 2 is a power of 2. Now, after that, I actually can make an inductive proof already. Okay. So I want to show that for every k after 2, that if up to 2, it was true that every integer in the range from first to that one, kth, was expressible as a power of 2, or as a sum of powers of 2, then the same predicate will be true about the next integer, k plus 1, namely that it too can be expressed as a as a sum of powers of 2 for some integers, and these have nothing to do with those, right? There is an existential quantifier here, and there is an existential quantifier here. This quantifier modifies this statement. This quantifier modifies this statement. These are two different statements. They're free to use local variable, essentially, right, under the universal quantifier in both cases. Well, we'll see that there is precisely some relation between these, and that's how we're going to achieve a proof. But what that relation is, we'll see. Okay, where is the predicate? The predicate is here. It's again a existential quantified expression. The predicate on n says that there exists distinct sequence of ij's, I1 to some im, such that n is equal to this expression. It's a existentially quantified Boolean formula. That's the predicate. Okay. The proof, my proof here will go by two cases. Case one, case even. So k plus 1 is 2k prime for some k prime. This is very nice. Because k prime now falls into this range. Why is it? We need to argue two things about k prime. That it's non-zero. Well, it has to be non-zero, because if k is greater than or equal to 2, this is a positive number, so k prime must be positive. You assume it's even, therefore k prime is an integer. So this inequality is checked. Now, is k prime smaller or equal to k? Well, it's twice less than this guy. So so it is smaller than k plus 1. Yes, so you're done. It is smaller than k plus 1, therefore it's at least as large as k. Right? At a border condition where k is greater or equal to 2, yeah, well, anyway, it's true. So because this guy falls into the range that about which I assumed by the strong inductive hypothesis that this predicate is true for anyone in this range, therefore it's true about k prime. Therefore k prime can be expressed as a sum of powers of 2 for distinct integers. And since k plus 1 is twice k prime, then this is true, right? K plus 1 is expressible like this. So all that happens now is that 2 goes up into all these exponents by adding 1 to each exponent, right? Because 2 to the a times 2 is the same as 2 to the a plus 1, right? So each of these exponents are going to be just incremented by 1. And all these powers are distinct if these i's, I1, I2, blah, 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 were distinct, right? Because incrementing each of them by 1 is still going to, incrementing by 1 is a one-to-one function. It doesn't create collisions. So if you started with the distinct guys, you end up with the distinct guys, because adding 1 is a one-to-one function. Somebody asks if k shouldn't be k plus 1 be odd. Oh my goodness, yes, I'm so sorry. That is a typo. That is a very dumb typo, and it's a typo. K plus 1 even, yes. Okay, well, let's go back to our slideshow. Oh, it fixed it. Do you have my slide back? I hope so. Okay, good. I meant k plus 1 is even throughout without noticing that I wrote the wrong thing here. Thank you. Okay. So, oh my goodness, and this is called case 1. It should be called case 2. If k plus 1 is odd, that's my second case. We'll fix that later, okay? That's case 2. Then k plus 1 is 2k prime plus 1 for some k prime. Now, if k plus 1 is odd, why is k prime greater or equal to 1? Well, k is greater or equal to 2. So this is the same as to say that k is greater than 2, is equal to 2. So k is equal to 2k prime. So we make the same argument just about k here. K is was positive, so therefore k prime is positive. Is k prime bounded above by k? Yes, very clearly, right? K is equal to 2k prime, so k prime is at most k. Right, k prime is actually half k. Exactly, right? So it's bounded here. Okay, so a little gymnastics to show that this bound holds, but not particularly, complicated. Although it could be puzzling at some border conditions. And if it is puzzling, maybe it's puzzling for a good reason. Your border conditions are incorrect. Perhaps you need to increase the number of base cases because these arguments that once you represent this falls into the correct range are actually incorrect. Okay, so do be careful with these conditions. So if you establish this, then you're in luck again, because now this falls into the range of my inductive assumption. So I can represent it as a sum of powers of 2, and therefore k plus 1, which is 2k prime plus 1, it's this, I just switch, 2k prime comes here, and all these are distinct. And what happened now? It's the same as here, right? So I use this 2 to increment each of these exponents. They're here. And what's a 1? It's 2 to the 0. And they're all distinct. Well, the fact that all of these guys are distinct exponents is the same argument as here. And that 0 is none of them, well, because they are at least 1. So none of them can be 0. Okay. So indeed, in the end, it's a simple argument. The argument, if you wanted to, rather than the argument, sort of inductive arguments go backwards. Like, let's try to argue that some number k plus 1 is representative of a bunch of 2's. Well, let's consider this number either even or odd. Then there is a very nice relation between this number and twice less. And it's either twice less exactly or it's twice less plus 1. And if this k prime here, right, is a power of 2, then this representation gives you a natural way of representing the target as a power of 2. You can think of this instead as a way to construct all integers as power of 2 going forward, right? And how would you construct? By a recursive procedure that, given some base of starting points, creates new integers. How? Takes the ones you have, multiply them by 2, and either leave them like this or add a 1. And you will create all integers that way as a recursive procedure that starts at a right and just takes any numbers you already have in the bag, and multiplies them by 2, adds them to the bag, and adds the following 2 things to the bag. For any number in the bag, it takes it, multiplies by 2, adds it, and multiplies by 2 and adds 1 and adds it. And you create all integers in this way. Another way to see it is that you can create all bit strings, all binary numbers, by taking a bit and doing the following procedure. Shift it to the left and add a 0 on the right, or shift it to the left and add a 1 at the right. That's exactly multiplying by 2 and either leaving the result or adding 1 to it. So all bit strings can be created in this way. That's pretty intuitive. I can create all bit strings by starting with a bit, 0 or 1, and then doing the following procedure recursively. shift to the left and stick in a 0 or a 1 and recurse. Okay, so we will see next week that this constructive way basically corresponds to recursive programming. You can, and the backwards way is an inductive proof that something is true, and the two are going to be working hand in hand, because recursive program creates, let's say, bit strings, and now you want to argue something about the bit strings you've created. You will use induction to do so. Okay, so you see how the two work hand in hand next week, and how this whole exercises in inductive proofs will actually apply to arguing stuff about the type of things that you will see in programming or in computer science, otherwise known, right? Where there are naturally recursive objects, like recursive algorithms, recursive, where we'll see data structures that appear very naturally and all over the place. And induction is actually a tool to argue things about these. I had some other proofs to go over in case time allowed, but I ended up going over these. So any questions? Can you also not think of this proof as a binary exists? So all numbers can be made in base 2 with strings of, yes, exactly. That's exactly what I was talking. Will strong induction be on the exam? Yes, yes. So everything in the first, I don't know how many weeks that was, but until this week. So I guess that's 3 weeks of material. So yes, and it's also basically homework 1, 2, 3. Right? Will there be a lot of induction? So it will be kind of spread, but yes, I mean, there will be induction, because this is the first time I'm using a format where there's only 50 minutes. So I guess there will be probably one inductive proof, right? We cannot fit more than that. So there will be a proof by induction. Practice test released? No. You have homework. So basic thing is, look, do stuff that like homework asks you. If you know how to solve these type of problems, you're good for the test. If you want to practice more of these type of problems, by all means, go to book exercises and practice more of these problems. So the first type of self-check is, can I do all problems from the homeworks? Other self-test is to well, pick problems from the exercises. Do a similar one. Test yourself on these. I left half or more of these open. The exam be proctored. So that's like, I guess I'm still not sure about is there software that allows us to do so that you can look at your Zybooks. I think that what we'll do is like that we will just ask you to do everything in front of the camera. So it is proctored in that sense, and but I'm not sure that we can lock your screen and allow to use Zybooks. And people asking whether this stuff is proctored sort of is disturbing, because like this really should not make a difference to you, I would assume. Okay, I mean, unless you believe that, you know, us watching you make a test is a violation of your privacy. I will stop recording.